So we're going to work a complete example of a DVAT problem. DVAT problems are problems where there is motion with constant acceleration. And in class and in the textbook, we have derived 4 different equations that describe that motion with constant acceleration. And they're listed here. The equation 1 you can see comes from the definition of acceleration, and it means that as long as a is constant acceleration, we will have a linear velocity time graph. Equation 2 comes from the midpoint equation. Again, if we have a linear velocity time graph, we can find the average velocity for any interval by taking the midpoint. And then we can use that average velocity halfway between the initial and final and multiply by time to find the displacement. So we'll call that our midpoint equation. Equation 3 can be derived by finding the area under that velocity time graph to find the displacement. And what we found is that the displacement is a quadratic function of time. So that implies that any position time graph will be a parabola, will be quadratic. Equation 4 is derived in the textbook. You can derive it by eliminating the variable t from one of these equations above and subbing it into a different equation above. So this one does not involve time. And this one I call the stopping distance equation for reasons that you'll see later on in the course. So we're going to use these relationships among displacement, velocity, acceleration, and time. So the problem we're going to do is from the Knight textbook. It is Chapter 2, Problem 47. And the problem reads, excellent human jumpers can leap straight up to a height of 110 centimeters off the ground. To reach this height, with what speed would a person need to leave the ground? So we're going to approach this problem and all other DVAT problems in a stepwise way. And I'm going to refer you to the problem-solving procedure that's posted on Canvas and was handed out in class. So we will go through these steps for the problem about the person jumping vertically. So the first thing that's very important that you understand for any problem is where does the problem start and end, and what happens in between. So this problem actually doesn't start until the person has just left the ground. And it ends when they're at their maximum height. And that's important because only between those two times is the person's acceleration truly constant, which is the assumption we're making for DVAT problems. So he's going to have a constant acceleration once he's in free fall and has left the ground. So in my solution, I'm going to indicate that when I start writing it up. Exactly where does the problem start and end? The goal of this problem actually is to find the speed with which the person left the ground. That means find the DVAT variable initial velocity. Alright, I'm also going to draw a diagram labeling the initial and final positions and velocities and a coordinate system. And I'm also going to label, as you'll see, the direction of the object's acceleration. Alright, let's do all of those 3 steps on a diagram. You can just draw stick figure diagrams. Make them big so they're easy to read. And there's my stick figure person who has just left the ground. He is now moving upwards, and I'm representing his initial velocity by an upwards arrow. And I'm supposed to define in words the initial and final places, so I'll just write a little phrase there. The initial is just after person leaves the ground. So that's where the problem begins. And then sometime later, the person is at his final position in the problem. I'll just indicate that. That's at the maximum height. And if you think about it, when he goes up and reaches his maximum height, he actually has to stop at that instant before he can come back down. Stopping means his final velocity actually is 0 at that position. All right, now I'm also asked in the problem-solving procedure to indicate the direction of his acceleration with an arrow. I'm going to try to focus this a little better. There we go. So this person's in free fall, and that means that at all times he's being pulled downwards, and therefore he's accelerating downwards towards the earth. So I'm going to indicate that with a separate arrow, and that is what we mean by the direction of his acceleration. Okay, so we've done the first 3 steps. I'm going to go back to the problem-solving steps. We get to skip steps 4, 5, and 6 for DVAT problems. We'll learn about those later in the course when we do some different kinds of problems. Alright, the next step is going to be to make sure we have our known information correctly with the right units and the right signs, because some of these DVAT variables could be negative sometimes, and if we needed to convert units we would need to do that now. So I'm just going to make a list of the knowns. Sometimes they'll be stated in the problem statement, sometimes they'll be implied. So we've already figured out that the final velocity is 0 meters per second. That was implied because he was reaching his maximum height at that time. Another known is the displacement, and that was given as 110 centimeters. I'm going to convert that to meters because that's the standard unit. So that is 1.1 meters. I just have to move the decimal place. The other known is his acceleration. If he's on Earth, near Earth's surface, anything in free fall will have a magnitude of acceleration 9.8 meters per second. So I'll just write that. That's the magnitude. I need to be careful about my plus and minus signs, and actually I forgot to put my coordinate system on the diagram, so I better go back and do that. That was part of step 3. So I can choose positive direction either up or down. It doesn't matter which way I do it, but I'm going to choose it up for this example. So that means anything that is in the upward direction is a positive number, and anything that's in the downward direction actually is negative, towards the negative end of my number line. So therefore delta x, which is the guy's displacement, that's a positive number because he moves up on the number line. However, the acceleration has to be a negative number because that's pointing down, whereas we define positive as up. Alright, so we've done step 7. We've got our 3 knowns, and 3 is what you will always need to solve a DVAT problem in motion in one for any of the unknowns.
Alright, step 8 says we're going to write down our basic physics principle. So we haven't done Newton's laws or work energy yet. We're working with DVAT equations. Alright, so we're going to write down a DVAT equation and then solve that for our unknown. By the way, the goal, I'll go ahead and write that down. The goal is to find VI. Find the initial velocity. Okay, so one of these DVAT equations will let me do that. And I need to look at what are my knowns and what am I looking for. So if I know VF delta x at A and I'm looking for VI, the simplest way to solve that is to use equation 4, because that has the 3 things I know and the 1 thing I'm looking for. I could do this problem in 2 steps. I could use a different equation and maybe solve for time first, and then go back and solve for VI, but it's fastest just to use this one because it's 1 step. So we're going to write down our DVAT equation. Equation 4, VF squared is equal to VI squared plus 2A delta x. We're going to solve it for the unknown. We don't put in any numbers. We're going to solve it
symbolically do the algebra without putting in numbers until you've isolated the unknown. There's one exception to that rule, which is if it makes the algebra simpler, you can sub in 0, because that helps you simplify the equation. And in this case, VF is 0. So you could sub that in if you want. All right, I'm going to solve for VI. I'm going to subtract 2a delta x from both sides, and then I'll do VI squared first. VI squared is VF squared minus 2a delta x. Now to isolate VI, I'm going to take the square root. And I have to be careful with my algebra because that could be plus or minus. And sometimes the minus sign is the one you're looking for. So start out by writing both, plus or minus, and then figure out which one is the correct answer. Or sometimes they're both correct. All right, then we're going to sub in our numbers. All right, so what I'm up to in the problem solving steps, I've written down my basic equation, I've solved it for the unknown. I haven't put in numbers yet, although I could have put in 0. So I've done my algebra. Now I'm going to substitute my numbers with their units and get my answer. So I'm on step 10. So this will be VF, I can sub in as 0. I will have the square root of negative 2. A is negative 9.8 meters per second squared. Delta x is 1.1 meters. I'll leave my plus or minus out there. And on my calculator, there we go. You plug that in and you find VI is 4.6 meters per second. Now, hopefully you know that we want to have the positive square root, not the negative one. And we should write a little reasoning there for that. It's positive because we know person is moving upwards initially. And on our picture, the upwards direction is what we call positive. So that's how we know. So we've solved the problem. That is the person's initial velocity. Okay, we should just check our answer to make sure it's reasonable. If you have a way to make sure that's reasonable. So that's a fast walking speed. So we can imagine that a person could jump that fast. It has the right units. It's in meters per second. All right, step 12. We might be asked to draw some graphs. I'm going to go ahead and do the graphs for this problem, just because it's a good example. And then step 13, if you did get help from somebody, you should write a note at the end saying who helped you, what you got help with. All right, so we're going to do the graphs last. We have most of the information. We actually don't have the time. So if I wanted to, I could solve for time and put that on my graph. That would be easiest to do with equation 1, because now I know VF, VI, and A. So let's go ahead and do that. I'm going to solve for time. I'm going to start with my DVAT equation. And then I'm going to isolate T. T is VF minus VI divided by A. VF is 0. VI we know is 4.6 meters per second. There's my minus sign from the equation. A is negative 9.8 meters per second squared. And if I divide that out, I'm going to get about 0.4 seconds. I rounded off a little bit, but that's the time. Okay. Last step I'm going to do is the graphs. I'm going to align those 3 graphs vertically so we can compare them. The top one's always going to be position, in meters. This is going to be time in seconds. The middle one will be velocity in meters per second. The bottom one's going to be acceleration in meters per second squared. And I'm going to make my time scale go up to 0.4 seconds. Okay. Now, the easiest graph to do out of these three is actually the acceleration one. Hopefully you recognize that, because this is a constant acceleration problem. So his acceleration was negative 9.8 meters per second squared because he was in free fall the whole time. So I can draw that as a constant value. The next easiest one is probably the velocity graph. All right, let me make a note here. We're always going to have a constant acceleration in DVAT problems. All right, we know the velocity graph is going to be a line, will always be a line in a DVAT problem. And so we just have to figure out where to start it and end it. Well, we know that the initial velocity was 4.6 meters per second, and the final was 0, and it's got to have a linear shape, so I can draw it like that. We have a linear VT graph, constant acceleration. The slope of that graph would be negative 9.8 meters per second because the slope of that VT graph is the acceleration. All right, the final graph is the position time graph. We learned that that's going to be a parabola or part of a parabola. So I know that the person starts at the origin, we'll call the ground our origin, and he ends at his highest point. And I know that that is 1.1 meters. So in between the origin and the highest point, he's going upwards, but he's losing speed the whole time. And the way we're going to show that is that his position time graph will get less and less steep. In other words, his velocity will start at a large positive number, 4.6 meters per second. So this position graph will have a large positive slope. But by the end, the position graph has to have a 0 slope because he is stopped and he is at his maximum height. So I'll try to sketch a part of a parabola here, something like that. Okay, so we've done everything there is to do with the problem about the person jumping. This was an example of a DVAT problem in one dimension, motion with constant acceleration. And make sure you follow your problem solving steps when you're writing up your homework. All of those steps